Hey, welcome back. In this video, we're going to talk about solving nonlinear systems of equations. Beautifully is that we have the same graphical representation of the solutions to the system being the intersection points of the two equations. And we also can use our exact same methods of substitution or addition eliminations to solve these systems. The differences are going to be about the number of solutions that we expect. Importantly, you've probably only seen linear systems of equations. When we have two variables, those are represented by two linear equations or lines. And we know that if they have a solution, a unique solution, there's only one unique solution, which is the intersection of these two lines, because obviously two lines in the plane can't intersect more than one point unless they're dependent, in which they're exactly the same line. Importantly, in the cases that you'll see in nonlinear systems, the graphical representations could be a line and a parabola. They could be a circle and a parabola. They could be a circle and an ellipse, or they could be two graphical objects called hyperbolas that intersect at multiple points. The important thing is you don't need to have a deep understanding of the graphical representation, though it can kind of help you sometimes when you're trying to check your solutions. All you need to do is put your head down and use exactly the same algebraic techniques that we've used with linear systems. Importantly, in this case, I'm looking at 2x plus y equals -5 and y equals x squared plus 6x plus 7. And again, in this case, this is going to be a linear equation or a line and intersecting a quadratic or a parabola, but I'm not going to think about this. When I'm analyzing this and thinking about method I want to use, I think right away I'm going to use the substitution technique because I already have one of my equations set equal to a variable. What I'm going to do then is I'm going to substitute y in this first equation with this equivalent expression of x squared plus 6x plus 7. And so I'm going to replace that in that place right there. So what that would give me is 2x plus y, but again, y in this case is represented by x squared plus 6x plus 7 equals the -5 right here. And again, at this point, the big difference is I don't have a linear equation which will have one solution. I have a quadratic, and I know that this could have no solution, one unique solution, or two unique solutions. But all I'm going to do is go about solving this. I'm going to set one side equal to 0 and then a factor or use another technique to solve this. So when I clean this up, I get an x squared over here. I get plus 8x. And then adding the 5 over to combine with this constant of 7, I get plus 12 equals 0. I'm going to then solve this by factoring. It looks like I can factor this, positive 6 and positive 2. So x plus 2 and x plus 6 are the factored version of this quadratic, which gives me two solutions of x equals -2 and -6. And then we know the solution to a system of equations are these ordered pairs. A point for x and y is a solution. I have two x's, and as you're going to see, what's going to happen is each of these x's will have an associated y value. I can find that by simply just starting with one of mine. So I'll start with the -2 first. When I have x is -2, I'll use this first equation. It seems like a little bit less work to deal with. I get 2 times -2 plus y equals -5. This is a -4. I'll add 4 to both sides to get y equals -1. And importantly, that gives me a solution. The solution is x equals -2 and y equals -1. Though that's not the only solution I have, I'm going to find another solution by using the x value of -6. And so we run through the same exact steps here, plugging in a -6 and solving for y. 2 times -6 plus y equals -5. Here I get -12. I'm going to add 12 to both sides to get y equals 7. Which gives me my second solution of x equals -6 and y equals 7, meaning then I have a solution set. So I had a set of solutions, more than one solution to describe here. The first solution is -2, -1, and the second solution is at -6, 7. And just to tie things together real fast, let's look at the graphical representation. And here, as we would expect, we have a linear equation and a parabola being intersected. The first solution that we see here is at -6, 7, and the second solution that we see is at -2, -1. Importantly, again, when solving these nonlinear systems, there'll be a crucial decision you need to make about how much work you're going to give yourself in the near future by how you're going to solve it using either the substitution or the addition or elimination. Again, for me, there were two factors that made me want to use substitution here. First, well, the second equation is already set equal to y. And second, y is linear in this first equation. Knowing that, like if this was y squared, I might try to avoid this because then I would be plugging in this 3-term quadratic and then having to square it. That's just a lot of multiplication. I'll have a lot of terms that I need to clean up. And in this case, since I saw this already set here, it was linear. I was like, okay, when I plug this in here, I'm going to get this quadratic that I feel comfortable solving. In our second example here, we have x squared minus 2y equals 8 and x squared plus y squared equals 16. Just so we know, this actually, graphically speaking, would be a parabola that hopefully is intersecting a circle. But that's not important at this point. Again, all we're going to do is put our head down and use an algebraic approach. In this case right here, I have a lot of squared, so I'm going to try to do something to keep from expanding too much crazy algebraic statements. Like for instance, if I was going to use substitution, I would probably solve this first equation for y and then substitute that in here. Though, when I do that, what I would get is this multi-term expression in for y that I'd be squaring, foiling out with things might get gnarly and messy. And I might end up with some like 4th degree polynomial equation that's going to be really hard to solve. I have to use some of those crazy techniques like the rational root theorem or something like that. And also, I probably wouldn't want to solve this for x because solving this for x would require a square root at some point, getting a plus minus. I'm going to avoid all that jazz. What I'm instead going to do is use the addition and elimination technique. And actually, I'm going to subtract these from each other. Or more importantly, how I like to think about it is I'm going to multiply this second equation here by -1 and add them together. So I'll write this all out. What I get is x squared minus 2y equals 8. I've unchanged that equation. When I multiply this second equation by a -1, I get -x squared minus y squared equals -16. And then I'm going to add these together. Importantly, by the way, and it really doesn't matter how you feel comfortable with this, I never think about subtracting two equations. I always think about addition. If I want to use subtraction, I'm always going to be multiplying by a negative. But the game here is why I multiply by a negative and why I want to do that is because these x squareds cancel. Importantly, when you're doing this, I wouldn't use addition and elimination to cancel these y's because these are not of the same degree and they won't cancel each other out. So this is x squared minus x squared, beautiful. Those cancel. But for instance, here, when I've got -2y and -y squared, these don't have the same exponent. They're not the same degree. They can't combine in any useful way. So when I have these two terms, I'm really just left with on this left-hand side is -y squared and -2y. Though on the right-hand side here, I can actually add these two constants to get -8. Now what I'm going to do, I have a quadratic in terms of y. I'm going to set one side equal to 0. I like not having a lead term that's negative, so I'm going to add these terms to that side to get 0 equals y squared plus 2y minus 8. And then it looks like I can use factoring here, and this becomes y plus 4 and y minus 2, which then gives me two solutions for y as y equals -4 and +2. So at this point, after that first little strange step of using addition and elimination on these x squared terms, everything is working out the same way as it did previously. I'm just going to find my solutions here. So when y equals -4, what am I going to use? Let me use this first equation. It looks a little bit easier. I get x squared minus -2 times y, which is -4, equals 8. This becomes x squared plus 8 equals 8. Subtract 8 from both sides to get x equals 0. Well, that's super easy. You can think of square rooting both sides to get x equals 0. Importantly, then again, what that means is that this gives me the solution when y is -4, x is 0, so I have a solution of 0, -4. Then I'll plug in my second y value of 2, so I get y equals 2, and again, I'll use this first equation here. I have x squared minus 2 times 2 equals 8. This becomes x squared minus 4 equals 8. Add 4 to both sides to get x squared equals 12. Now when I square root both sides here, I can't forget this plus or minus, giving me two solutions here. So I get x equals plus or minus the square root of 12. I can reduce the square root of 12, thinking of this as 4 times 3. The square root of 4 is a 2. This radical reduces down to plus or minus 2, the square root of 3. So something interesting happened here. When I plugged in y equals 2, I didn't just get one solution. I have two associated x values. And importantly, each of these solutions come in these ordered pairs. This means I have two ordered pairs with two different x values, but the same y value. The two solutions I get from this y value right here are 2 root 3, comma 2, and negative 2 root 3, comma 2. Therefore, the solution set for this nonlinear system of equations is 0, -4, 2 root 3, comma 2, and negative 2 root 3, comma 2. And just to step back and look, if we look at the graphical representation of the system, we see that we have this parabola here intersecting the circle described by the second relationship right here. And you can see those three intersection points at 0, -4, 2 root 3, comma 2, and negative 2 root 3, comma 2. Final thoughts when attacking these nonlinear systems. Again, number one, it's exactly the same technique. You're looking for ordered pair solutions. The difference is you're not just going to have one unique solution if you have a unique solution. We also have cases where we have no solutions and infinite solutions like we did previously, though they're not as common in these nonlinear systems. And in this case, I use addition elimination and I used it for the x squareds here because those are terms of the same degree that will cancel when I add things together. Again, it's important to notice that if I tried to eliminate the y's using elimination, that wouldn't have worked here because I don't have a y squared in this equation right here. Eliminating the x squareds, whatever I get, I plug these both in. Importantly, when you plug these in, you shouldn't expect always just to get one solution. You can have one or more solutions to the equations that you can get, depending on the original relationships that you're given in your system.